So the next session is on the data challenge, which we conducted this year, similar to the last year. The theme of this year's data challenge is generative AIs, which is one of the hot topics in the recent years for synthesizing medical thermal data set. We all have open source data sets that are there in thermal images, but the number of thermal images that we are finding on open source are very less. So this year data challenge involved asking participants to use these existing data sets or their own data sets to develop Gen AI algorithms so that we can synthesize these data sets, which could help in solving critical problems in the healthcare industry. Some of the prominent open source data sets that AIIMA has included on the website include onchocerciasis thermal imaging dataset from Niramai, COVID-19 thermal screening dataset from Niramai, breast thermal imaging dataset from Visual Lab, thyroid imaging dataset from Visual Lab, and plantar dataset from AIIMA and a chronic wound multimodal imaging database. We have received two presentations. We have two accepted manuscripts under this data challenge. The first paper is from Bharath Govindaraju from Niramai Health Analytics with the title Generative Artificial Intelligence Approaches for Synthesizing High-Fidelity Breast Thermal Images. Over to you, Bharath.
Yeah. Sorry, it's my screen.
Yes, it's visible.
Good evening, everyone. So I'm from Niramai Health Analytics. I'll be presenting another generative artificial intelligence approaches for synthesizing
Your audio is too feeble, Bharath. Maybe you can speak it loud.
Is it better now?
Can you speak again?
Yeah, is it better now?
Yeah, a little better, yes.
So good evening. So today I'll be presenting work on generative artificial intelligence approaches for synthesizing high-fidelity breast thermal.
Maybe you can switch off your video, Bharath. You can switch off your video and try.
Yeah. So we're presenting our work on generating artificial breast thermal images under
It's the same.
Oh, I'm sorry.
Sorry, please go ahead. Sorry.
Sorry, is it better? Does it feel better now?
Yeah, this is better.
Yeah.
Oh, thanks. Sorry for the glitch. So breast cancer remains the most of the prevalent malignancy among women worldwide. So WHO reported about 2.3 million new cases of breast cancer in 2022 and about 670,000 related deaths globally. Well, the current gold standard for breast cancer detection is mammography screening. It has a few limitations, such as low accuracy for women with dense breast. It requires some high-skill expertise, some interpretation of the images, economic feasibility in some low-income countries, and so on. So the breast thermography, which measures the breast surface temperature, has emerged as a non-invasive alternative for breast cancer detection and has gained attention in the last decade. So earlier, the manual and subjective interpretation of thermal images was an impediment to its adoption, but now with the AI-driven algorithms in force, so there are studies which have shown that it enhances the breast cancer detection accuracy, interpretability, and reliability. So now, why do we need generative AI in breast thermography? So there's a lack of large-scale and high-quality data sets in medical imaging research. Thermal imaging, breast thermography, is emerging modality, and which is still not as widely used as part of a routine clinical practice, which results in a limited repository of the breast thermal dataset. And this data paucity actually hinders the advancement of AI algorithms. So one of the solutions is to say generate synthetic data sets. So if we learn from, if you look at other imaging modalities, so there have been studies that have shown generated mammography mass images, which was used to improve the detection rates by 5%, and artificially generated histopathology image patches improved classification on cervical histopathology by about 6%. So given that the synthetic datasets have shown some potential in improving the detection rates, so we now look at our approaches for generating synthetic breast thermal datasets. So we investigate and compare three prominent generative AI algorithms: variational autoencoder, generative adversarial networks, and the latest state-of-the-art being the diffusion networks. And for all these experiments, we used the Frechet inception distance as the metric to compare the quality of synthetic data with respect to the real data sets. I'll just briefly go over the architectures that we used, experimented with. So first is the deep convolutional variational autoencoder. So the variational autoencoder has two parts, the encoder part and the decoder part. The encoder tries to map the input image into the parameters of statistical distribution, such as the mean and variance of a Gaussian distribution. And then we sample the point from that distribution, and the decoder tries to reconstruct the image back. So these images are the actual images from our experiment. So VAE seems to capture some of the high-level details of the breast, like the silhouettes of the breast, but not so much of the final details that we would like. The second experiment that we did was with generative adversarial networks, which has two parts, the generator and the discriminator. So generator and discriminator trained in an adversarial fashion where they kind of compete with each other. Generator tries to produce the fake image or a synthetic image, and the discriminator is trained with the generated image as well as the real image, and is trained to identify which is real and which is fake. And over the course of training, we expect the generator to get better at generating synthetic images that closely match the real images. And in this case, generator and discriminator are both deep convolutional networks. Generator has a sequence of transpose convolution blocks, and discriminator is based on a modified VGG 19 architecture. The last architecture that we tried was the latest state-of-the-art diffusion networks, denoising diffusion probabilistic model, which was a paper published in 2020. The main principle behind DDPM is we sequentially add noise to our input image in the forward diffusion process over a series of time steps. In our case, we use the 1,000 diffusion time steps. At the end of this, we expect the image to be turned to a complete noise, like pure noise. And then we learn to denoise the image sequentially, one step at a time. And for this, we used a denoising UNet. UNet is a network that has an encoder-decoder structure with skip connection, and it can capture complex multi-scale features, so which is ideal for this complex denoising process. So we used a four-stage UNet architecture. So another difference between earlier two networks, VA and GANs, and DDPM is that in DDPM, we go from pure noise to image over a series of steps. In this case, for us, it was 1,000 steps, whereas in VA and GAN, they try to generate a real image from noise in just one step. Evaluation metric, we used evaluation metric called Frechet inception distance. So Frechet inception distance is a widely adopted metric for medical and non-medical synthetic image generation. So the Frechet inception distance tries to estimate the distance between two distributions. So in our case, so we try to generate a bunch of images from our networks, and we have a set of real images. So we pass all of these images through an inception network and try to extract features from intermediate layer. And then we set a multivariate normal distribution on each of these synthetic features extracted from synthetic dataset and features extracted from the real datasets. And the Fresh inception distance gives us the distance between these two multivariate normal distributions. So the ideal value of FID is 0, which indicates the two image sets are very identical, and higher the value, higher the divergence between the two data sets. For our experiments, the data set comprise of...
Bharath, 2 more minutes to go.
Yeah. Dataset comprised of anonymized breast thermal images from 102,459 participants, which was collected over a 6-year period. So for each participant, we collected 5 distinct views. This ensured comprehensive coverage of our breast region. And for data processing, we used min-max normalization, which ensured the pixel values are all in the range of 0 to 1. We applied very minimal data augmentation because we wanted our networks to learn the real artifacts and not the augmented artifacts, so they were kept to a minimum. And all networks use the ADAM optimizer with a batch size of 4 and with different learning rates. So in the results, so we generated 50,000 synthetic images from each of the 3 networks, and we had a separate set of 50,000 real images, and then we compute the FID scores on the Gaussian distribution that were fitted on each of these pairs. So from our results, we can see that the lower the FID score, the better. So the DDPM model, denoising diffusion probabilistic model, achieved the best FID score of 18, even though the inference time was much longer. VAE had the fastest inference time. So these are some of the examples of the generated images. So that we can see that VAE captured some of the higher level details, but not so much of the finer details. GAN was better, but the images were still noisy. The last row was the DDPM images, which were high quality data, which seemed like a much better quality, and they closely resembled our training data set. So in conclusion, we, having completed the experiments with 3 different architectures, we see that the diffusion model achieved the highest image fidelity, despite taking much longer inference time because of the iterative nature of the image generation. GAN offers a good balance between image quality and speed, but this produces some noisy image. And VAE captures high-level details, but lacks in image quality. I find these results are significant as there's no existing literature on the performance of these networks in synthesizing breast thermal images. So from our findings, we can see that the better to focus on the diffusion models, given that they gave the best FID scores as a future work. And the FID scores that we obtained were consistent with the FID scores that were obtained for other medical image problems, which range from 20 to 150. Thank you.
Thanks, Bharath, for the wonderful presentation. Any questions? Anyone, if there are any questions, you can raise the hand or unmute and ask questions. We'll just take one question in the interest of time. Yes, Raghav, you were saying something?
Yeah, I was curious about what was the size of the real data set used when comparing the FID between the generated images and the real data set?
50,000. For all, it was 50,000 data sets.
Okay. So if there are any questions, you can post it in chat, and Bharath, in the next 10 minutes, please do reply to those questions.
Yes, thank you.
Thank you again for the wonderful presentation. With this, we move on to the next paper on about the validity of using DC GANs for data augmentation in breast thermography segmentation by Carla Estefani, Universidade Federal Fluminense, Brazil. Carla, we can't hear you.
Hello,
Yeah, we can hear you now.
can you see my presentation?
Yes, please continue.
Okay. Hello, my name is Carla Stephanie, and together with Professor Aura Conce, we developed this work on the use of generative AI to increase the database of thermal image to segment the breast. And the title of your work is about the validity of using DC games for data augmentation in breast thermography segmentations. Um, uh, Before I begin, I apologize if my pronunciation is confusing. I still don't master the language. My friend and Professor Combs will translate the questions for me in case I don't understand. So, um, this topic is my presentations. I will take a little about what I wanted to do, what we did, and what the results were. So the data set used was a sample of a 16:4 frontal image because the quality of the others was not good. The acquisitions of images were approved by the Research Ethics Committee. Um, we made a unit model with a little data we had, but as expected, the model couldn't learn due the due to the size of data set. The dataset we used was a sample of 16 for frontal image because the quality of the others was not good. It was divided into 14 images for training, 10 for validations and testing. So, um, uh, and how can you increase in the database? We so So we started thinking about generative AI and how you could use it to generate a thermal image, but maintaining the control of the body. The choice one, the choice one, and I forget the result. The result for this model is not good. The accuracy in first moment is very short. Sensitivity and specificity too. Continuing, the choice one ones this again, which are class of neural network that are using their generative new data, resemble to the training data, so as image. This type of neural network wants two main components: the generative and the discriminator. The the generative is received a random vector and with it created a synthetic image. The discriminator in turn evaluates about the real and synthetic image in our iterative process, into which can no logic differentiation between the two images. During the generator trees to for the discriminator be creating increasingly realist image. I'll the discriminator trees to improve its ability to distinguish between real and synthetic image. It is continuous process of competitions and mutual improvements along the DCGN, generative highly realist image over time. In the first test, we chose the training for 1,000 epochs, uh, and these were the results. The images were not bad, but we wanted better quality. So we ran two sample network again with 10,000 epochs. The quality of the image improved, and we also noticed with the of loss functions that after 5,000, the network no longer learned anything. So we can run an experience with 5,000 apples. To evaluate the quality of generated images, we use the fractions inception distance and Jensen-Shandon divergent metrics, which are calculated this way. When these same mysteries are close to zero, it means that the quality of the image is good. The Fiji metric is one scale region for 0 to infinity gives us 2.93, and for the GSD metric we give 0.105. For both metrics, there is great similarity between the real and synthetic image. Now we would have a new problem, which would be how to label the synthetic image, how to segment the generated image. After creating these games, each one's necessary to develop a process that will facilitate the segmentation of this newly generative image. We using the original demo image for illustrations plus gamma corrections once applied to the image for whitening. Then we applied also threshold to open a mask of the patient's body, and finally we multiplied the two to obtain the contour. After this point of the white mask once calculated, and while and all white points above the midpoint and 35 pixels 1 units away were excluded.
Shall I have 2 minutes? Please complete the presentation in 2 minutes.
Okay. To exclude it to square only the largest set of grouped pixels once keep finally, and to find to the curvature of the breast we used it to x-coordinated the of midpoint blue and calculated the difference between and x-coordinate of each point, both for the left and right sides. This result is 2 points that mark the contour of the breast in relation of the contour of body. To complete the automated key and segmentation process without using a neural network, the following exclusions were made using the image with the outline of the body in the breast. We excluded the points that are above 35 pixels from the central point. Then after find the 2 points, the mark and the breast curvature. We draw and two lines, one 45 degree and 135 degree. This line lead to the end to image, excluding all the white pixels in that radiations. For the figure shows some examples where the automatic is not perfect. There are some unwanted edges and lines. For patients whose breath bouldering is not overlooked, where generative using the trained DC gains and 200 images were chosen for which the generative mask were significantly better. We manually removed one strained line and one wanted picket. The figure shows examples of how the image the generated masks looked after this manual adjusted. The results using UNet to train this network, we used a set of 200 image generated to be trained this again. Since the most important aspect is borrow structure, we augment the data by inverting on or storage database. The result is
Carla, can
very
you speak in the next 1 minute? We're already delayed by 2 minutes. Can you complete the presentation in the next 1 minute?
okay. So evaluating the results of UNet, which the original images base, there were much better results than using only the original data. And the result is very, very good. For accuracy is 19%. And comparison between results, the first wrong shows the difference between, then there is little details that goes from one mask to the others, but the results are relatively good. Comparison sums measurements before and after applying DC games, we can see that the metrics have increasing significantly. Thank you.
Thank you, Carla, for the wonderful presentation. It's very good to see the power of Gen AI in improving the overall results. I think we have seen a significant improvement from 30% accuracy to a 90% accuracy with the use of generative AI here. We're open for questions. Any questions from the audience? We'll just take one question in the interest of time. Okay, we have one question from Raghav. Did the final training contain any of the real images or only synthetic images were used?
The images synthetics for using for training these games, and for UNet too. The image is real for note. The image is real for using for training these games. After after created images synthetic, um, we using the images synthetic images for training unit and using images real for validations unit.
Okay, that's good. So if there are any questions, I think everyone can post it on the chat. And Carla, please reply to those questions in the next 10 minutes. Thank you, Carla. Again.